Hello, welcome everybody to another video. We're going to be just talking about the rules of differentiation and see how we can use them to your advantage, okay? I'm pretty sure you guys already know these rules, so I'm just going to briefly go over them, trying to explain how the dynamics of each of the rules work. And then I might give you some hints on how to use, some rules to your advantage to help you solve a problem faster. I've noticed a lot of people recently have struggled with chain rule, and I want to make sure I go over that to ensure that you guys can see the rule the way I see it, okay? I'm going to try my best to explain it. Followed up with that, I'm going to try to talk about a little bit about the implicit differentiation and see how you can use that to solve and take derivatives of exponential functions. So that's coming up next, okay? And without further ado, let's get on to this. So in this video, I'm going to talk about the 5 rules or I should say the 5 major rules of differentiation, okay? And I'm just going to name them out first, then I'm going to go through each one of them one by one, okay? The first one you guys probably know is called I'll tell you what that kind of basically means in just a second, what it is. The second rule will be called the addition subtraction rule, okay? This will help us take derivative of functions which are made by addition or subtraction of another functions, okay? That's that. Then we're going to start on some beefy ones. The first one's going to be product rule. Relatively speaking, a lot of people are comfortable with this, where product rule is pretty easy to memorize and apply in certain scenarios, as compared to the fourth one, that's quotient rule. Okay. Very effective tool, but sometimes there are ways to avoid them. I'll show you examples of what I mean, and then we can just go on those. And the last one is the chain rule. Okay. For this one, you need to understand what composition of a function means, okay? So we'll talk a little bit more about that. I'll just present my analogy of how I think things look like, and then we can move on from there, right? So I'm going to try to explain each of these rules one by one in a brief kind of way by giving you an example and giving you pointers on some questions where you can use this to your advantage, and then we'll move on from there, okay? So the constant rule, as the name suggests, is basically a rule of constant. Okay? And the way you would write that thing, how I would write it out, is if you're taking a derivative, okay, and the notation is clear. When you say d by dx, then you're taking a derivative with respect to x, okay? So watch that out. When you're taking a derivative of, let's say, a function, f of x, that has a constant k in front of it, okay? So I'm taking the derivative of k times f of x. What that means is you can, because of the constant rule, you can use this k and pull it outside and then multiply by the derivative of f of x. Okay, so you can take the derivative of this function first and then later on multiply by the k. Okay, so that's like a very easy kind of way of saying it, but I can show you some examples. Very simple example. Let's say I'm taking a derivative of 5x cubed. Okay, I know the function is x cubed and there's a 5 in front of it. You can treat the whole thing as a function, but I'm going to treat it as a constant rule. Okay, so as the rule suggests, what you can do is you can take the 5 outside first, take the derivative of the remainder function, and then go from there, right? So here, this derivative from power rule, which I don't really formally want to like it as a power rule, but I'll tell you what it is. Power rule will tell you that the derivative of x to the power of n with respect to x will be n, x to the power n minus 1, and this rule is only valid for x values as long as they're not equals to -1. Okay, I'll explain a little bit more about that power rule, but if you apply that, most of you guys already know this answer will be just 5 times 3x squared. So this is the derivative of this function. And now when you simplify it further, you get 15 squared as your final answer. It's a very easy rule, and sometimes people, tend to forget what this multiplication means and how it works out. So I want to give you one more example to show you where this is beneficial and how a lot of people might just have a intuition to use quotient rule first, but this is much easier than that, okay? That example would be like this. So second example, will be if you want to take the derivative of a function. Let's say that's x squared over 16, right? So if you've run the rules before, you know that the first intuition is to go with quotient rule because it has a fraction, right? But you can always rewrite this. If the denominator of a fraction is a constant, then you can always rewrite it like this, where I can write it as 1 over 16 times x squared. Where now this guy is nothing but a constant, right? So we can apply the constant rule here. So this would mean that you want to pull out this 1 over 16 first, multiply by the derivative of x squared. This way, because of power rule, derivative of x squared is very easy, and that's just going to be 1 over 16 times x. And now when you multiply them and simplify it, you get 2x or 1 over 16. And then you get x over 8. So this could be very beneficial if you're working with functions that look like fractions, but they have essentially a denominator, which is a constant, okay? So you don't really have to go through the whole quotient rule way. But of course, if you want to do it, you can do it. You know, it's just beneficial to use power rule here, okay? That was the first one. Second rule, very straightforward, so I'm not going to take too much time here. Add, subtract rule is as follows. If you're trying to take derivative of something, okay, which is either addition or subtraction of two separate functions, okay, then what you can do is you can take the respective derivatives first, like these, and then add, subtract those as required, okay? Very easy thing, so I can give you an example. This does work out in a lot of ways, but you might not even see it, but I'm going to try to show you. So let's say I'm having a function that's x squared plus 2x minus 4. Okay? So if you have this function, you're basically having a function that's composed of addition or subtraction of 3 individual functions. Okay? So by the rule, what I can do is I can take the derivative of x squared, add the derivative of 2x, and then subtract the derivative of 4. So I can take the respective derivatives and you know, apply these respective operations to those derivatives afterwards. Okay. Derivative of x squared with power rule would just give you 2x. Derivative of 2x with the constant rule and the power rule, if you want to be very specific, would just be 2 times 1. And negative, sorry, my bad. Negative or derivative of 4. 4 being a constant would mean that it never changes. Okay, that's literally the definition of a constant. And when you try to take the derivative of a constant with respect to x, well, it never changes, hence the derivative is always going to be 0. So for any constant, if it's 4, pi, e, whatever you have, they're always going to be 0 because of the rule that they never change. Okay, and now here you have 2x plus 2, and that's the final answer to that derivative. Very easy rule. Just want to point out the thing about this, if you want to take a derivative, let's say they try to confuse you. If they want to tell you to take a derivative of pi e with respect to x, well, don't get fussed up because pi and e are basically just both constants. So it's going to be 0. Okay? And that's how you kind of rule out this possibility. That's second rule. Okay? Moving on. The third one is a product rule. And as the name suggests, this rule is going to be used when you try and take the derivative of something that is basically composed of multiplication of 2 separate functions. Okay, then what you can do is you can apply the formula where you take the derivative of the first guy, keeping the second function as it is, multiplied there, with a plus of keeping the first guy as it is times the derivative of the second. I'm saying guys because that's how I learned it, so it's always on my tongue. But for you, those guys are just functions. Okay, so don't mind my easygoing language. So that's the rule. Okay, so now an example of how this would be used would be, let's say you're trying to take a derivative of a function, x squared e to the power of x. So you clearly see there are two functions that are being multiplied here, right? First one being x squared, and the second one being e to the x, right? So when we're going to take the derivative of these guys, what we're going to do is we're going to take the, as the formula told you, take the derivative of the first guy, so I'm going to keep it in the formula first, and keep the second guy as it is, so just multiply it right there. Plus, now I'm going to keep this, the first guy as it is, and times the derivative of the second guy. That will leave us to this from the power rule. Very simple, 2x times e to the x plus x squared. And this derivative, you should probably know this because e to the power x is a very popular function. The derivative of e to the power x is just e to the power x as well. So I would say there's no rule, but by memory or, you know, trust in what people have done before you. So just trust them, and that's how we figure this out. Okay, so simplifying this further, you get 2x e to the x plus e to the x squared. And that's the final answer for taking the derivative of this function. Very straightforward rule. I'm pretty sure most of you guys are comfortable with that. And you just have to try to stick to the definition of functions, right? Now we're going to move on to a little bit more difficult one, which is quotient rule. Some people have it memorized, but I'm going to try to make sure that I try to put it out, okay? So as I suggest, the quotient rule is applied when you try to take a derivative of something that's composed of two functions in a rational expression, which means in a fraction, okay? So the rule follows like this. So you would take the denominator, square it, keep the denominator like that, take the derivative of the numerator, and subtract basically the first function as it is and derivative of the denominator from it. Okay, that's the formula. Sometimes what we do is we use a notation of writing this dy by dx of f of x as just f prime of x. You've probably seen that. So this rule in a more condensed form will look like g of x with f prime of x minus f of x with g prime of x divided by g of x whole. If you guys want to be very lazy, just write them like this: gf prime minus fg prime squared. Okay, so don't use the x if you want to be very lazy. That's the rule, right? So we can give you an example. You're trying to take the derivative of the same that function that we did, but now in the fractions. So x squared over ex. Right? If you want to take the derivative of that, so if you use the rule, you got to first of all write the square of the denominator, so e to the x squared. Then we're going to keep the denominator as it is, take the derivative of x squared. So x squared prime. Okay, that's that notation. I'm going to take the derivative in the next step. For now, I'm just going to write it out. That subtracted, you got to keep the x squared as it is, times the derivative of e to the power x. So e to the power x prime is what I'm going to write there. So once you have it in this format, we can expand it out. So you have the numerator becomes e to the x times 2x because the derivative of x squared is 2x minus x squared times derivative of e to the power x is just e to the power x. And then you have on the bottom, you have e to the power 2x. I can simplify that like this. And then most of the time you'll be okay when you leave the solution just like this, okay? And there's not going to be any consequences to this. So that's why I want to make sure that you understand this is what's happening, okay? As a side gig, I want to take 1 second to show you how you can deduce the quotient rule from the product rule, okay? So remember, the product rule was here, where we want to say that if you have two functions that are being multiplied like this, where you here, you can do like this. So before we can actually deduce this rule deduce the quotient rule from product rule, we have to make sure we understand what chain rule is, okay? So that's our final step. And this is where I want to bring up a silly analogy that I learned this rule with. The analogy of Russian dolls, okay? Before we do that, we need to understand what composition is. Okay? A very simple mathy example is if I choose my f of x to be x squared, and if I choose my g of x to be maybe e to the power x, And then if I like to write the composition of f of g of x, that would mean that I'm going to take whatever g of x is and plug it in place of x in this function. Okay. So when we do that, what are we going to get? This function will be having, so you're going to take the f of x that was x squared, so I'm just going to keep that exoskeleton off it and plug in e to the x, right? That's how we look at that. So when you were able to solve all these, compositions, I want you to be able to see that, how you can look at a function and deduce what's its composition like. So if I give you an example here, okay, of a function, let's say we have e to the power of x squared. That was an easy example, where you know that this is a composition of, an exponential function and an x squared function, where when x squared function is plugged inside an exponential. That's the deformation of this function, right? Let's go up one step ahead and see what we can get here. So if you have, let's say, sine x or sine of ln of x, okay? So here you know the composition is made up of two functions, one of them being sine x, one of them being ln x, and then you see the ln x being, plugged in inside sine of x. It's kind of like, Russian dolls. If I give an example like this, let's say you have square root of e to the power of x squared. So this is where you have to see there's more than, two functions involved here. The first function would be square root of x. The second function will be e to the power x. And the third function will be x squared. Okay? And you know that x squared is being nested inside e to the x, and then all of that has been nested inside the square root of x. Okay? So that's how we unfold a composition of a function. Sometimes it might be not that easy to see, like for this example, 1 over e to the power x. Okay? This function is composed of two functions, where you have the first function being 1 over x and the other one being e to the power x, and so you can nest them like this. Okay? And then you can have different complicated problems just arising from the same expression, where you might have, even worse questions like this. So I'm going to have a gigantic function. I'm just going to wing anything out. So I'm going to be like square root of sine of e to the power of, 3x plus 4 squared. Maybe you have this function, right? So now if you were to deduce what's been nested inside, let's start from the outside. The outermost function is square root of x. The one inside that is sine of x. One inside that is e to the power x. And what's been nested inside e to the power x is basically an x squared. That would be a little bit tricky to see, because if you see that, e has been raised to something squared. So the function is basically x squared. And what's been inside the x squared function is 3x plus 4. So it's been nested by like 5 functions. So if you take that thing, you plug 3x plus 4 into x squared, take that, plug it into e to the x, take all of that, plug it into sine of x, and then take all of that, plug it into square root of x, is what would lead you to this function. Okay? So this is like a little way of how I think a function is made and composed in a way. So you got to make sure which rules and how they apply in this effective way. Okay, just gonna go over a bunch of more examples to make sure you guys understand. I'm gonna say if this function is here, 2x whole squared. Okay, this function is composed of x squared and another function 2x, where 2x has been nested inside x squared. Very easy to see now, right? If you have, let's say, 1 over 2x. Okay, this function could be also seen as 1 over x nesting a 2x inside of it. Okay, similarly, if you have e to the power x squared or e to the power 2x, both of them could be written as e to the x nesting an x squared inside of it, or an e to the x nesting a 2x inside of it. Okay, very easy. These are from the common examples you can think of, right? So that's how we decide there's a composition. Now, when we know what the composition is, we can actually introduce the rule. Okay, the rule of taking derivative of functions that are composed like that would be like this. If you want to take a derivative in which an outer function is a function f and the inner function is a function g, okay, then what you'll do is you'll take the derivative of the outside function f while keeping the insides as it is without being touched, okay? And then followed up by taking the derivative of the inside function. So we'll be taking the derivative of the inside function g of x, being multiplied by that. So the chain rule basically, keeps on going one nesting inside one at a time and then keeps on taking the derivatives, right? So for an example here, if you were to take the derivative of e to the power x squared, we know it's a composition of e with an x squared being nested in there. So the outer function is going to be e to the power x, and then the inner function is going to be x squared. I'm going to write in like here so you can follow along there too. And this has been nested. So I'm going to take the derivative of the first guy, which is e to the x, but we're going to keep the input as x squared. We're not going to touch it, okay? And luckily we know the derivative of e to the power x is just e to the power x, but we have to keep the input, whatever was nested before, so it's going to be x squared. That's the first step that we have, multiplied by the derivative of the inside. Now the function that's inside e to the x is x squared, so the derivative of that is just 2x. And that's how you compose a derivative of a function like e to the power x squared, okay? I want to take a derivative of a function that's like more than two compositions to kind of make sure you understand the concepts. So let's go back and take the derivative of, let me cook up a function. Let's do to the power 3x plus 4 to the power of 2. Okay, this one's a little tricky, and this is a composition of three functions, okay? Where the first function, I'm pretty sure you guys can see, is an x squared function. Inside of that, we have e to the power x, and inside of that x, we have 3x plus 4. The 3x plus 4 got plugged into e to the x, and all of that got plugged into an x squared, okay? So we have to do this rule thrice, but we got to make sure we keep the compositions going. The first time, we're going to tackle the outermost, which is the x squared, okay? And the derivative of x squared is just 2x. It's going to be 2 times whatever was plugged in the place of x squared, and that's all of this, right? So we're going to move it out here. So 2 times e to the power of 3x plus 4, and that's it. The first step, okay? Then we're going to move on to the second guy. The second guy is e to the x. So take the derivative of e to the x would mean you have to take e to the power of the same thing. So the thing that was nested inside e to the x was 3x plus 4. So keep that like that. Don't touch it, okay? We're only going to tackle like one exoskeleton at once. And then followed by the last derivative would be taking the derivative of 3x plus 4 because that's the last thing that's nested, okay? And derivative of 3x plus 4 would just mean it's 3 because derivative of 3x is going to be 3. Derivative of 4 is going to be 0 because it's a constant, right? So you can say we're compounding multiple rules to get to these derivatives, okay? Right now, it might seem a little bit off topic, but it will get easier as you practice more and more questions. Try to logically reason your way. And if at any point of the time where you're confused and fighting how a function is composed, which rules you're going to use, and what's going on, you can always reach out to me, okay? But now that's all the composition of chain rules that we have, right? So now, as I was talking about deducing the quotient rule from product rule, and I'm going to show you how I do that, okay? So if you're taking the derivative of, a function f of x divided by a function g of x, what you can do is you can write it like this. Function f of x being multiplied by a function 1 over g of x. Okay, where this function is basically a composition of 1 over x and whatever the g of x is. You see that, how it's a composition? I'm pretty sure you guys do that, okay? 1 over g of x is a composition of 1 over x and where g of x is plugged in the place of x, okay? Now keep that handy because we're going to use that. Right now what I see is a function f of x and a function 1 over g of x being multiplied, so I can use product rule, okay? If I apply the product rule, then I'm going to get taking the derivative of the first guy keeping the other guy as it is. The other guy is 1 over g of x, no problem. And then plus keeping the first guy as it is, taking the derivative of the second function, which is 1 over g of x. Right? That's what the product rule means. This one will be easy. We're going to keep it there. We can just keep it as a derivative f of x. This will be a little bit interesting because taking the derivative of 1 over g of x with respect to x would require you to use chain rule because, as we suggested, that 1 over g of x is a composition of 1 over x and g of x. So by chain rule, this guy would mean taking the derivative of the outer function first. And outer function is 1 over x. If you guys don't know, I'm just going to put it out here. You want to take the derivative of 1 over x with respect to x, then you can treat it as x to the power minus 1. With this and apply power rule, you get negative 1 x to the power negative 2, which is basically negative 1 over x squared. Okay, so I just did it on the side so you guys can, keep it handy. So we know the derivative of the outer guy is negative 1 over, x squared. So by chain rule, this will be negative 1 over, keeping the inside as it is, squared. Remember, when you're doing chain rule, you don't touch the inside, right? We're dealing with the outside function first. So that's the derivative of the outside. And then the derivative of the inside would just basically be derivative of g of x divided by x. That's what this is going to be. Now that we have this function, I'm going to put everything else back here to make it into a notation properly. You can't really add these functions just yet because if you see that, you have terms in each one of them. And if you want to combine them under a common denominator with a condensed notation, I'm going to do that. So this could be written as f prime of x. And times that by g of x would just mean dividing by g of x. That's the condensed form of the first guy. On this side, you have a negative f of x times the derivative of g of x with respect to dx could be written as g prime of x. And multiplying by 1 over g of x squared would just mean dividing of g of x. That's what this is. So now, since this is the condensed form of it, if you want to take the LCM and combine these two terms, what you would need is you would need to multiply by g of x here and the g of x in the bottom. Because if you do that, then your new denominators will match up, right? So now when you take the LCM, the total denominator will be g of x whole squared. The first term will be g of x multiplied by f prime of x, because that's what you get when you do the multiplication of these two terms, in subtracting f of x with a g prime of x. And this right here is the definition of quotient rule. Okay? It is a little bit notational savvy, so if you don't get it, no problem. But just wanted to put this out because some people might have this question. To deduce the quotient rule from product rule, you need chain rule. There's a lot of rules just going back and forth. Just wanted to make sure you guys know how to do this, okay? But don't stress out too much on this. Right now it might seem overwhelming, but most of the time when you do practice and when you're logically following your way through and cross-questioning what's going on, we will be able to make sure that we're able to solve the expressions much easily. And with that being said, I want to take a second and show you how to take a derivative of a function. Okay, quickly, let me pull that out. So we're going to be working with a function that is basically going to be function f of x times two times e to the power of x over 2, and then 1 minus e to the x. The bottom, you have 1 plus the x whole square. So this function is pretty nasty in terms of what kind of rules it might use to work it out, okay? But if you take patience, you'll be able to see those pieces like I do, okay? So first things that I can see, that this function is a fraction, where the denominator is also another function. It's not a constant. So we need to use quotient rule, okay? That's for sure, because it's a fraction, right? Now when I look closely at what these functions in denominator and numerator are, well, in the denominator, it's a composition, okay? It's a composition of what? It's a composition of, an x squared function where you're nesting a 1 plus e to the x side of it. Right? So this is kind of a composition that you have to see. That's the denominator. If you look at the numerator as well, a numerator, this guy is also composition. This is a composition of e to the power x and x over 2, where x over 2 has been nested inside e to the x. Okay, so I know that's a composition as well. Moreover, the numerator is basically a multiplication of this function with this another function. So we also need to use product rule somewhere in this work, okay? Because of the product rule, right? And to make sure that we understand that these compositions are there, we also need to use chain rule to get rid of all these things, okay? So I'm going to go step by step, apply these rules, and try to show you how I work this question out, okay? I'm going to go to a new space to kind of make sure we have a continuous working spectrum. So rewrite the function to 1 minus e to the power x over 1 plus e to the power whole square, okay? So when I'm going to take the derivative of this function with respect to this guy, I can see that this 2 is just a constant being multiplied, so I can pull it out of the whole operation and take the derivative of whatever's left. So it'll be e to the power x over 2, 1 minus e to the power x, divided by 1 plus x whole squared. That's what I'm going to be dealing with. So because this is going to need a quotient rule, I'm going to apply that. Okay. If you don't remember quotient rule, make sure you open it up to kind of get a feeling of what's going on. So with that step, the derivative of this twice. Now I'm going to try to use the quotient rule to write it out. Okay. I'm going to take the denominator and square that first. Remember, this was already squared, so squaring that will cause it to go to the power of 4. But we'll do that later. Just going to follow those steps. So it'll be 1 plus e to the power x squared with 1 plus e to the power x whole squared sitting there times the derivative of this term. So the numerator is over 2. Okay, that's the first term. And now we got to subtract, keep e to the power x over 2, 1 minus e to the power x as it is, times the derivative of 1 plus e to the power x whole squared. I know it's very nasty, but you got to follow along with me. I'm going to try to move this all a little bit closer to that. Close the bracket. That's the first step. Okay, so we'll apply the quotient rule. Now I have to simplify the later parts and take the respective derivatives after that, right? So here, we already know that this needs product plus chain. So we're going to see that. And we also know that this guy needs a chain rule. Okay, so let's solve these individually and then plug them into the equation, right? So the first derivative we're going to work on is I'm going to use the green to isolate for those ones. So the first guy we're solving is taking the derivative of x over 2, 1 minus e to the x, right? So it's a multiplication of e to the x squared, x over 2, times 1 minus e to the x. So by product rule, I can write it like this. I'm going to take the derivative of the first guy, keep the second guy as it is, add the derivative of 1 minus e to the x, keep the first guy as it is. So now this is where you would need chain rule because it's a composition of e to the x and an x over 2, right? So that's chain rule. And to do this, this will be a simple add subtract rule. Okay? Special. So with that being said, to take the derivative of e to the x squared, x over 2, we need to take the derivative of the first function, which is e to the x. So the derivative of that is going to be just that same thing. And don't touch the inside, just keep it as x over 2. Multiplying by the derivative of x over 2. And because of the constant rule, x over 2 could be written as, 1/2 times x. And 1/2 could be pulled outside of the derivative. Then you would get basically a 1/2 times derivative of x, which is 1. Okay, so that's that. That's the derivative of the first guy. And now we have 1 minus e to the x and a plus. Now, taking the derivative of that function is just going to be very easy. Derivative of 1 minus e to the x is going to be derivative of 1 minus the derivative of e to the x. So derivative of 1 will be 0, and minus the derivative of e to the x will be negative. Negative e to the x. This times e to the power x over 2. Simplifying this further will lead you to e to the power x over 2 with 1 minus e to the x. And then here you'll be left with a negative e to the power x times e to the power x over 2. Okay, you can of course simplify it further, but I'm just going to keep it in this format because I still have to work it out. So this is the first piece of the puzzle. So we found out this guy. Okay, we're not really done. We still have to solve for the derivative of 1 plus e to the power x whole square. Okay, so let's do that on the next page and see what we can get. So to get the derivative of 1 plus e to the power x whole squared, we know this is a composition of x squared with 1 plus e to the x nesting inside that. Right? So by chain rule, we got to take the derivative of the outside function first. Outside function is x squared, so the derivative is going to be 2 times whatever was inside. So 1 plus e to the x was inside, so just keep it like that. And then we're going to multiply by the derivative of 1 plus e to the x, which could be done by easy add and subtract rule, which is going to be derivative of 1, which is 0, plus the derivative of e to the x, which is. So that way, if you simplify it, you're going to get 2 times 1 plus e to the x times e to the x. Okay? Or twice e to the x, 1 plus e to the x is the derivative of it. So now we have both the pieces of the puzzle solved, right? So we got this guy already solved here, and we've got this guy solved on the next page. We can finally write the derivative of the main function. Okay, I'm going to do that right now. It'll be a little messy, but you got to bear with me. The derivative main function is going to be twice. So 1 plus e to the power x squared will stay there. 1 plus e to the power x whole squared stays. And now this portion here, the derivative of e to the x over 2 times 1 minus x, will be replaced by this guy. Okay, so let's do that. That would be just e to the power x over 2 divided by 2 with 1 minus e to the x. Then negative of this guy. The negative e to the x times e to the power x. That's the derivative of the numerator, right? And then we have a subtraction sign. And then we're going to keep this guy as it is, x to the power e to the power x over half. E to the power x over 2 times 1 minus e to the x. That's the numerator staying there. And this portion right here, where you have the derivative of 1 plus e to the x squared, will be replaced by this guy. So that's going to be times 2 e to the power x, 1 plus e. That's that. And all of this is being divided, by e to the 1 plus e to the power x whole squared. So okay. If you want, you can go a step ahead and try to resolve this expression, which I'm going to do because of whatever, reason I think. But I don't really see any point of actually further simplifying this expression because it won't get you anywhere, okay? But I'm going to do it because, it's my kind of like a duty to do it. So let's do it. 2 So if you see, all these terms have 1 plus e to the power x, because this also has 1. Oh no, not this one. This is 1 plus e to the power x, and we have 1 plus e to the power x here. So I could factor that out. And I also can factor out one more thing. This has a term, e to the power x over 2. This also has it. This also has it. So I can take those all out of this and have it this way. So the remainder that's left inside the bracket would be 1 plus e to the power x, because I only factored one of them. So out of the square, only one of them will be moved out. And then out of this whole thing, e to the power x over 2 has been gone. So we'll be left with 1 minus e to the power x, 2 minus e to the power x. Okay, that's the terms left from the first part of the numerator. The later part of the numerator, this guy is gone, and so is this guy gone, right? So I'll be left with negative 2e to the power x, and then 1 minus e to the power x. Okay, that's what's going to be left with. So this is going to be the closing, and then you have a division by 1 plus e to the power x to the power of 4. So now, because one factor could be cancelled, this and this will be to the power of 3, the answer could be simplified further to this guy, 2 to the power of 2, 1 plus with the bracket simplifying to just being 1 minus 3. Don't worry if you don't get how I got this. This is because of algebra. So if you patiently do it yourself, you'll get the same result too. Minus 2e to the power x, 1 minus e to the power x. That's the whole numerator. And in the bottom, 1 plus e to the power x whole cubed. And this is the final answer. The reason why I took this example to kind of go over right now is because it covers all the rules where you can figure out what's going on. Okay. The way you would want to do this is very cumbersome, so it's broken down in steps. I'm going to revisit what's going on super briefly to kind of make sure everybody's on the same track with me. Okay. We saw this function. This function was a hideous composition of a lot of rules. So the first thing we saw, this is a fraction with a non-constant denominator. So we need to use quotient rule. That's done. The numerator itself was composed of two functions that are being multiplied, so we have to use product rule in that quotient rule as well. And then we also know that all these functions, there are two functions here, e to the power x over 2 and 1 plus e to the x whole squared, which are compositions. So when they're compositions, you got to use chain rule as well. So we know that we had to use this. So we're going to apply the first thing that we see. The first thing we apply is quotient rule, because the outermost thing is a fraction. So when we apply the first quotient rule here on this expression, we end up with this term. Very nasty, very big, but we can work it out. And then after that, in those derivatives, as the quotient rule was applied, we required another couple derivatives, which are right here. Those couple derivatives needed to be done using, separate rules. So this would require product rule and a chain rule. So that's what we did here. All of this work is for this particular piece. And then for the other particular piece, we move the work on this next page because it requires chain rule as well. So once we have those pieces composed, I plug those pieces respectively here and here. And once they're back into this place, I just simplified it, which is not really required, but I just wanted to make sure I present whatever is possible for everybody. Okay. And that's how you finish off this problem, which requires you to solve this whole question. Okay. So with that being said, this is done. I can move on to the topic away from rules and try to show you a little bit about implicit differentiation. Okay. So moving on. In implicit differentiation, what we're going to do is we have to understand that the way differentials work is you have to be very careful that when you're taking a derivative of a function, which variable are you taking the derivative with respect to? Okay, we can try to avoid certain things by being cheeky, but I'll show you what it means. But if you have, let's say, a function here, I'm going to try we're going to call this function f of x, where it will just be, let's say, x squared. So we easily know this is a function of x, no problem. And no questions really asked on this, which is fine. But I want to make sure that when we work it out, that the problem is whenever I give you like a weird function, let's say ln of y. Well, this is a function of y. Right? And how would you take a derivative of a function of y, but with respect to x? This is the question we're trying to answer. Okay? If you want to take a derivative of a function that's not matching up with the variable, what you do is you would break this down into taking the derivative of the function with respect to its own variable. So because f of y was a function of y, I'm going to take the derivative with respect to y, and then I'm going to multiply it with taking the derivative of this. Okay? Because if you see that technically these cancels out, so what you're left with is just taking the derivative of that function f of y with respect to x. But we like to break it down in this format, okay? So that's what we're going to do when we encounter functions like this, okay? And why we really need that is sometimes we might have to perform derivatives on functions that are not functions of, basically x anymore, okay? So one example I would like to give you here is, let's say I have a function. We have an equation here. So it's not really a function, it's an equation. And the name of these kind of equations are called implicit equations. Okay? These equations basically give you a relationship between x and y, but they don't necessarily tell you, if one is a function of the other, okay? And in these questions, if I was to ask you what's going to be dy by dx, I was to ask you this, it's going to be hidden somewhere here in this function. So what we're going to try to do is take the derivative of this equation implicitly. Okay, what I mean by that is I'm going to take the derivative of both sides with respect to x. Okay, I can do that. So when I take the implicit derivative, both sides with respect to x, let's work with the easy side first. This is literally just going to be derivative of x squared plus derivative of 4, which is going to be just 2x, because the derivative of 4 is going to be 0. So that side is very easy. That's nice. In this case, you're in this caught up situation where you're trying to take a derivative of a function like ln y, which is not a function of x. Okay, so what you got to do is you got to take the derivative of that function with respect to y first. So I'm going to write it out here. This will be taking the derivative with respect to y of ln y, and then timesing it by dy by dx. So that's how the equation evolves, okay? And when you're here, taking the derivative of ln y with respect to y is just going to give you 1 over y. Because derivative of ln is just going to be 1 over that thing, so this is how we get it. And now you have dy by dx on this side equals to 2x. When you simplify this equation by isolating for dy by dx, all you do is you multiply both sides by y, so you get 2xy. And that's literally what the solution of this equation is going to be. Okay. These derivatives occasionally involve an x and a y, so don't be very skeptical of how it looks like, but that's literally how it's done. Okay. And now why do we even care about this is to take derivatives of functions that are exponential, and I'll show you how. Okay. Let's say you're working with a function and it's given by like this. It's like, let's say y equals 2 to the power of x. Okay. We can't really take the power rule and apply it right here. If we want to find dy by dx, we can't really do that because the variable is in the power. Power rule only works if a variable is raised to a constant number. In this case, it's the opposite. A constant has been raised to the variable. So this kind of function is called an exponential function. Okay. And e to the power x is just like one of those functions too. But 2 to the power x is also an exponential function. To work with these, what we do is we first of all remove its characteristic of it being an exponential function and convert it into an implicit equation. How we do that is we take natural log of both sides. That would give us ln of y ln of 2 to the power of x. Okay. And by the properties of ln, you can bring this x out and multiply it here. So this equation will be ln of y times x times ln of 2. Where ln of 2 is going to be a constant, so don't worry about that. Okay. Now this right here is an implicit equation because it's describing a relationship between y and an x, but it doesn't really tell you what's going on, right? As a who's a variable, who's a function. So this is an implicit equation. Now here you would take the derivative of both sides with respect to x implicitly, okay? And when you do that, what are you going to end up here with the classic situation of taking a derivative of a function that is not a function of x, okay? So here I'm going to try to take and write it out in a format of implicit differentiation. So I'll take the derivative of ln y with respect to whatever the variable it's defined with respect to, and multiplying by the derivative of that variable with respect to x. Okay, that's the derivative of the left side. On the right side, you'll be taking the derivative of x times a constant. So by the constant rule, that derivative is just going to be, constant times derivative of x, which is just 1. So it'll be ln 2. That's what just effectively the constant is going to be. Okay, times 1, the derivative of x. So with that being said, if you isolate for, let's just simplify this first, the derivative of ln y with respect to y is always going to be 1 over y. And if you simplify this expression to isolate for dy by dx, again by multiplying both sides with y, it'll be like this, right? This is the equation. And then if you multiply both sides by y, you get dy by dx as y times ln of 2. And if you know originally y was just 2 to the power x, if you plug it here in place of y, this derivative would be very easy. It will be dy by dx equals to 2 to the power x times ln 2. And many of you guys already know that the derivative of 2 to the power x is going to be just 2 to the power x times ln of whatever that number is. So this is how we deduce the expressions of functions that we're working with, okay? I thought it will be helpful for you guys to see what's going on in this format, and hopefully had an opportunity to learn some things. Of course, this stuff might be overwhelming too. If you have any questions regarding any of the content that I covered and want to ask me out, just hit me up with those questions, and you know where to find me. Thank you very much for watching, and I'll see you in the next one.